is we agreed that she would do all of the recordings.
Okay.
She wasn't here.
Okay.
Okay.
Yeah, I think
It looks like it's recording now, so maybe I'll start
great.
just a couple of
Okay,
words.
please. Yep.
So Kaan and I actually met at an OSA meeting the first time. And, it was funny because it was really a small session on augmented and virtual reality within OSI, which is really a niche. And, it's somehow I end up being there at that meeting that year. And because it wasn't just a meeting just on virtual reality or something like that. And it was kind of nice for Kaan, first of all, to come to that meeting and give a talk. And I was really so impressed with his talk. I was really enjoyed it. I felt like his talk made, the meeting was for me, to go. And then so I approached him afterwards and we started discussing, what he did and, the what's going on, what has been going through history and stuff. We were talking about that. And since I think we've been basically, still collaborating a little bit, like Kaan reviews a lot of papers also that from the community. So I feel like he's like a really great example of someone who, has been working in industry and was really made some huge contribution to the community in research and so on. So I really commend you for that, Kaan, for everything you're doing in the community and really appreciate your contribution. So I just wanted to say that. And thank you for coming to our class symposium here. Mm-hmm.
Thank you, Jenny, for your kind introduction. I'm also always fascinated by your papers, especially ones about the freeform optics. It's a very promising direction, and I myself also trying to get into such domains and follow your work, basically. Yeah.
Thank you.
Thank you, Jay, for this very kind introduction. I appreciate it. And let me give the formal introduction. Hi, everyone. I'm Müjdat Çetin. I'd like to welcome you all to this lecture on augmented and virtual reality. This series is organized by the Gergen Institute for Data Science and River Campus Libraries at the University of Rochester and is supported by the National Science Foundation as part of a PhD training program on augmented and virtual reality. As Janik mentioned, today we are extremely pleased to host Professor Kaan Akşit. I met Kaan when he was in Rochester for a symposium. I think it was back in 2018. Now Kaan is an associate professor at University College London in the UK. Before joining UCL, he was a senior research scientist at NVIDIA Research here in the US. His research interests are at the very interesting intersection of light and computation. So this includes computational approaches in imaging, fabrication, mobility, and displays dedicated to augmented and virtual reality, as well as 3D vision with and without glasses. Kaan received his BS degree in electrical engineering from Istanbul Technical University in Turkey, his MS degree in electrical power engineering from RWTH Aachen University in Germany, and his PhD degree in electrical engineering from Koç University in Turkey. He's the recipient of many prestigious awards, despite being a junior researcher in this area, including the Emerging Technologies Best in Show Award in SIGGRAPH 2019 and 2018, the DC Expo Special Prize in SIGGRAPH 2017, and Best Paper Awards in several conferences, including IEEE VR 2019, ISMAR 2018, and IEEE VR 2017. Truly impressive achievements, Kaan. With that, let me hand the mic to Kaan for his lecture on next generation display technologies for virtual and augmented reality applications.
Hi, everyone. Thank you for having me here today. Special thanks to Müjdat, Janik, and Caitlin for inviting me in the first place and hosting me in the first place. So, as Müjdat mentioned, I'm an associate professor at University College London. In this talk, I will be exploring next generation display technologies for virtual and augmented real applications. Before I dive deep into the topic, allow me to take a moment to give you a brief introduction about myself. So I joined University College London in the beginning of this year, where I will be forming my new research group as a newly appointed associate professor. Previously, I was a research scientist at NVIDIA, and I joined NVIDIA in 2014. I helped forming a new research group dedicated to virtual and augmented reality applications. 2010 to 2014, I was part of Optical Microsystems Laboratory at Koç University, where I got my PhD degree. I worked with Hakan Ürey. I conducted research on 3D displays with and without glasses, and also on wearable projection devices. During my PhD, I took an internship at Disney Research Studio in Switzerland in 2013, where I worked on visible light communications. And I got my master's degree from RWTH Aachen. It's located in Germany, where I worked on electrical machines and power electronics. It was a different era for me, basically, at those times. So during my master's, I took a year-long internship at Philips Research in the Netherlands, where I worked on medical sensing optics. This was the moment where I got introduced to optical sciences, basically. And I received my bachelor degree in Istanbul Technical University, where I worked on designing and building solar cars. And in fact, some of these solar cars went into races in Australia in World Solar Challenge. Beyond these experiences, I am and I have been collaborating with multiple institutions worldwide. Here you see a melange of their logos. And after this fast introduction, I can now go back to the topic of displays. Let me start by asking this question. Why the world needs better displays or better visuals in the first place? There's a very simple answer to this question. According to MarketWatch, a website on finance news, in 2018, American adults spend more than 11 hours per day simply interacting with the media on the screen, and that's up from 9 hours 32 minutes just 4 years ago, 2014. And spending time in front of a display isn't something only for adults. Many children at early ages spend time on displays. So it won't be wrong to say in this case, improving experiences with displays and visuals has a big potential for a valuable impact on other people's lives. In fact, as I'm telling you all these things, we are looking at visuals on a display and communicating through the display. So this device is a big part of our lives, our health, and our way to communicate, and our way to be productive in life. So let's look into the future. If you imagine a future where displays will be nowhere and everywhere, augmenting tools to get us connected to the other people, or tools to let us be more creative at our work, displays will be within our walls, our windows, our cars, and our eyes. Displays with the right interfaces and user experiences will assist us in many situations. The impact of displays in the future will help us to transform our society into a global society. Future with displays is bright and illuminating. So at the current day, the general consensus in the industry and the academia is that the next generation display technologies will be targeting virtual and augmented reality applications. Virtual reality provides a simulated experience of a similar or different world while completely blocking the real-world image. In parallel, augmented reality blends the virtual content, virtual visuals with the real world. So these new devices dedicated to a new type of computer-generated graphics is still evolving. I think these products are true engineering marvels. However, VR and AR are still not a big part of our lives. I believe there is a very long way to go, and this isn't where we should stop. To understand why we are at the very beginning, we need to first build an understanding on how these virtual and augmented reality displays work in the first place. So let's understand how virtual reality tries to mimic the real world by actually understanding how we observe things in real life. Here you see a human eye on the left-hand side and a tree at some distance on the right-hand side. Light coming from the ambient is bouncing off the surface of that tree, and the eye, an optical instrument, samples a bundle of incoming light rays onto its retina. This is the point, the retina is the point where rays converge inside the eye. An optical imaging device, eye, basically images point A onto the retina using its lens. Depending on the distance in between the eye and the tree, that lens inside the eye can adjust its focal power. So beyond focus, note that illumination levels of real life can vary greatly in brightness. There can be a great number of various different colors in a given scene. So a simple step for mimicking real world is to place a display in front of the eye. If you place that screen really close to the eye, then eventually you enter to the regime of near to eye displays for virtual reality. And the problem is solved and end of the presentation, right? But eventually no. And there's a good reason for this. Displays directly used in the near eye regime would be far from ideal. A quick experiment would be to take your mobile phone and put it really close to your eyes. You will only see a blurry image. So how do you make this work in this case? How do we observe that screen that we place in front of the eye so that we can see clear visuals? A conventional virtual reality near eye display at the time of this presentation uses a magnifier in front of a screen. And that magnifier magnifies the image on the screen and place it to some distance that we can accommodate, we can focus on. So to be a bit more accurate in this description, for an observer, things will look flat as in this image, and the display location is fixed. This particular design is more or less able to generate a single flat image in optical means. So it will be fair to say current virtual reality near eye displays do not support different optical depth levels with this given configuration. Now we know how to build a VR display. Let's see how we can build an AR display. So jumping from VR to AR is straightforward. A common augmented reality layout relocates the screen to an off-axis location, as shown in this figure, and places a semi-transparent, semi-reflective mirror in front of a user's eye. This type of half-silvered mirror is also known as beam combiner because it combines the beam from the real world and the beam from the display. There are multiple different alternatives for a near eye display optical design when it comes to augmented reality. For the sake of time, I will skip all these. I will leave up to you to go ahead and find out about how they work. But I want to just stress that among those four major alternatives, there is one which we have invented in the past. And I want to start talking about that design at a later stage of my presentation. So before jumping into the research, let's also list the challenges in the field of designing near eye displays, the next generation computer graphics platform. So it won't be wrong to say all of us see the future as an all-in-one computational display, taking both advantage from hardware and software with the highest possible efficiency. Challenges for a computational near eye display can be overall summarized as follows. The human visual system spans approximately 190 degrees field of view. In some military literature, this is even greater. If you want to test it yourself, like you can just put your fingers like this and put it sideways, you'll be able to see your fingers still, although you're gazing at some other location in the far away. So we have a really large field of view. A near eye display has to mimic this in order to provide the true immersion. And the human visual system can adapt to large brightness variations. Examples like stepping out from a dark room to a sunny outdoors are challenging cases, for cameras at least. In contrast, human eye does a pretty good job in terms of adaptation. So the human visual system also has a unique color perception combined with various levels of brightness support. And again, a near eye display would require to generate those colors and brightness levels. The human visual system has 20/20 visual acuity. To explain you what this means, if you look at some target at 1 meter away from you, that 1 arc minute is referring to 1 divided by 60 degrees, which would translate to 300 micrometer resolution at 1 meter away from your eyes. So the smallest feature you can basically resolve. And to give you some sense about what does 300 micrometers means, a thickness of a hair is half the size of that. So we are efficiently good at resolving things. A large eye box is also needed in near eye displays. Typically a 20 millimeter by 20 millimeter plane is considered. So the eye box is the physical location where you can perceive the visuals. As an example, in a typical desktop display, the eye-box is large because you can move to any locations you want, and you can still see the visuals from different angles. So everything has to be compiled in a small package. We need a form factor that enables daily usage, long-term usage, and we are also asking for ergonomy, right? Like it has to be comfortable to wear. So power and processing capabilities has to be good, at least as good as a smartphone for long-term usage. You cannot expect a supercomputer to be connected to a near-eye display, so you have a limited computation. That's also another thing to consider. How you can improve the computational resources. This is a valid question because there can be multiple different cases. Like maybe you want to generate graphics that is super realistic. How do you calculate that with a given limited computation? Or if maybe you want to stream a content and you want to do something along the lines of distortion correction or depth correction or gaze tracking and something similar to these things, it would again require the computational power to be present in the system. Beyond all these explained problems, there is also the big problem of lack of optical focus cues in the near eye displays. It's a major problem, and it's known as accommodation divergence conflict in the literature. You typically experience the same problem in the 3D movie theaters. Everything is sharp at the screen, but with the 3D glasses, objects are displayed at different depth levels. They can be inside the screen or outside of the screen, closer to you, right? Without correct focus cues, only by changing the disparity of left and right images, as in the movie theaters, you will induce some error because things will only look sharp at the level of the screen, but not at the intended depth levels. So basically, in a 3D display, eyeballs rotated as in this image, but the location of the 3D object is not matching where the things are sharp, so it's causing you to feel dizzy when watching 3D movies. So maybe before moving on, I should also mention that this is the same problem in augmented reality. It's even larger in augmented reality because there is the real world as well. So you want things to look sharp wherever you gaze at, for example, or your application has to support the depth levels that you're interested in a scene. So in order to resolve all the introduced challenges, my research was focused on near-eye displays for VR and AR in the last 6 years. So results of our research led to several different publications, and in the process with my collaborators, we developed multiple near-eye display prototypes as shown in this slide, and some of these are awarded with Best Paper awards and returned home with awards from exhibitions like ACM SIGGRAPH's Emerging Technologies show floor. And of course, most of this work was conducted while I was an employee of NVIDIA. So I got this common question like, why NVIDIA is eager to develop new type of displays? The answer is quite simple. If you invent the display, you know how to drive it. And NVIDIA is a graphics card manufacturer, so they want to know how they drive the displays in the future as well. So that's also part of their businesses. So I will now go ahead and highlight those 3 projects as one mega project dedicated to augmented reality. This is because those 3 projects are highly integrated to each other. They complement each other and they can be all integrated into a single body. So to form basis, for this proposal, maybe we should talk a little bit about how does one simulate the light. As you guys already might be familiar with, light is an electromagnetic phenomena, which means it has an oscillating electric field and a magnetic field that are perpendicular to each other. In many cases, light can either be described with rays or it can be described as waves. So those 2 approaches basically define the characteristics of your computational display design. And using ray or wave simulations, you can end up having different kind of solutions. Many different solutions have been proposed in this respect, and they are all targeting one major problem, divergence accommodation conflict. So they can be broadly classified as holographic displays, light field displays, varifocal displays, focal surface displays. Holographic near-eye displays treat the light as waves, and a true holographic display typically modulates both phase and amplitude of that electric field that we talked about. Therefore, it typically requires two screens, one for amplitude modulation, one for phase modulation. There are also variants that uses only phase modulation, of course. While multifocal displays, light field displays, treat light as rays, therefore neglect the cases like diffraction, which can limit the resolution of an overall display. All of these near-eye displays are typically complex in terms of hardware design, requiring multiple display elements to be present, therefore increasing the cost. Also, it demands a good amount of computational resources for calculation. I would describe those type of displays as futuristic displays that will start to be more practical in 5 to 10 years time frame from now on. So without going into much details, focal surfaces are also offering an exciting opportunity, but for the time being, I will say that the hardware part of such displays require a good amount of research to get to a practical implementation. The varifocal displays offers the least amount of hardware and software complexity with just a single display. So in the last 6 years, our bet was on varifocal near-eye displays due to its practicality in design and offering a solution for near-eye displays at a time frame of 2 to 3 years from now. Varifocal displays are likely candidates as next-generation displays. Our understanding of a varifocal display is aligned with Padmanabhan et al., in which, to address different depth planes, either the screen or the optics has to move, because as you move one of these components, the flat virtual image will change its location accordingly. Such relocation can be arranged by active optical components like moving lenses or displays, liquid crystal lenses or flexible lenses. In such a configuration, we are also making the assumption that a screen has to switch its depth based on the gaze information of a subject. This can be achieved using off-the-shelf eye trackers as done in the literature. And using the state-of-the-art computational blur methodologies in computer graphics literature, one can also represent parts of the scene that has to be out of focus and can even help to drive accommodation of a person, of a viewer, as described in this chroma blur work in 2017. Current vision science also favors varifocal mechanisms. As you can see, the recent studies concluded that varifocal systems can provide user performance and visual comfort. On the other hand, speed requirements of a varifocal system is not so demanding, thanks to the large latencies in the accommodation state change of the eye. So, adding these findings together, we started our journey towards identifying a new varifocal layout. In parallel, the main lead in VR near-eye display business, the Facebook Oculus, showed a product candidate based on varifocal displays in 2018-2019 timeframe, which is named as half-dome prototype. In the last Oculus Connect, they even announced and promised better versions of it coming in the next years. So varifocal displays is very likely to happen as a product at the near future. But let me take you to 2017. At the time frame before Oculus or any others showed their varifocal demos, we were working on this new varifocal display idea for augmented reality rather than virtual reality. Note that multiple forecasts out there also indicates that augmented reality will have a much bigger market than VR, and augmented reality is often perceived as the next step after VR. So let's understand this proposal. Let's follow the light path and see how this is working. A light engine, basically a projector, shines an image on a surface in front of an eye. That particular surface is unique and novel part of our proposal. It's a see-through screen that we have invented. Our see-through screen diffuses the light towards ambient only, not to the eye. So the diffused light from our see-through screen is relayed back into the eye using a conventional beam combiner. And this is a half-silvered mirror, as mentioned before, so it can some portion of the light just goes through, some portion of the light just bounces back into the eye. So an observer looking through such an optical system would see an image at some virtual depth. So by moving the beam combiner, the Hall silvered mirror, we can change the depth levels accordingly. And virtual images can be positioned at different locations in depth using gaze tracking in parallel. So overall, such a proposal opens a path to on-axis paths, because you can now place the screen in front of the eye and you don't have to deal with off-axis properties in optical design anymore. Now you can just work with the on-axis optical components that are off the shelf and doesn't really require you to be super precise in matching the requirements for the optical design. So this improves the simplicity aspect of the eye-box properties and field of view resolution and computational complexity. We have identified 3 different see-through screen candidates that can work for our proposal. A backlight of a conventional liquid crystal display contains dot pattern diffusers. We tried using such screens as a see-through screen. When the light is projected on such a screen, of course, you see these dots and some of the image is basically missing. But if you start rotating that, you will immediately end up, because of this temporal accumulation, you will immediately end up with a full image. So we can call this solution as cheap and dirty. Like you can, if you have just $5 and you want to make a see-through screen, that might be the way. So second candidate that we have identified is called a polarization selective diffuser. We got some samples from a company called Mito, Japan. This is a special liquid crystal based see-through optical element. It just diffuses the light when it's with the correct polarization. And we found that these films are good, but they can offer a very limited screen size as shown in this images. So we moved on to finding a better, much better solution, and we choose the path of analog holography. So we basically experiment with thick holograms. Here you see a captured photograph from our optical layout from that time using this diffusing holographic optical element, which is recorded in-house. And in our assessment with the holographic optical elements, we observed that they are the best performing medium with good see-through characteristics with negligible haze. So we can say our winner is the holographic optical elements. And for more on diffused holograms, this is a really good paper that can give you more about how one can record a holographic optical element and how one can make it a diffuser screen. So let me bring you to the final implementation of our proposal. So here you see a photograph of it, of course. For making this happen, we used a 720p 60Hz liquid crystal on silicon-based pico projectors per eye. So we used in-house built see-through screens based on holographic optical elements, as we discussed. And we designed in-house curved beam combiners using Xenox material. And we built a mechanical system to move the beam combiners back and forth, as shown here. And we designed and built and 3D printed parts using Formlabs printers. To drive all these, you need a graphics pipeline. At the time, we derived an OpenGL-based render, and we coupled that with the gaze tracker so that we can drive the display as intended. Using the shown testbed and visual targets, we benchmark varifocal capabilities of our display, and we find out that we can change the camera focus to different depth levels, and our display still continue to support good resolutions, as shown here. To read this correctly, from left to right, we are showing different depth levels. At each different depth level, we have a different target that is in focus, and we bring the display to the correct focus. And we can do this quite fast, in the order of like 400 milliseconds. We later on even found a way to make it even faster, which I'll be talking about in the next slides. Using a standard protocol of slanted edge MTF, we evaluate the display resolution at the time, and we find out that the best performing case was for 4 diopters, which is 25 centimeters close to the eye at 17 cycles per degree. And the worst case was 8 cycles per degree at 1 diopter. To give you a sense about like what these values are, like how do we compare it with the existing displays and so on. A typical virtual reality display that you can buy right now is in the ballpark of 5 to 12 cycles per degree. So our display prototypes provides a moderate level form factor, and we found our display can work with good brightness levels suitable for direct sunlight conditions. And we tried this at a very sunny location at California. So our display prototype also supports 60 degrees monocular field of view, opening the possibility to extend field of view to larger values, all thanks to its on-axis geometry. So at our paper, we provided much more details of our technical evaluations and also design space. I won't be going into details of that, but I'll just say that it's available at our paper. Later, we asked ourselves, what if that curved beam combiner that we used doesn't have to move so much? What if we can replace it with something else that is stationary? And we tried to look into different solutions, and we played around with the idea of changing the curvature of a beam combiner actively on demand. And here is what happens when you do that. Like if you change the curvature of a display's beam combiner, you'll immediately get images at different depth levels. So we invented an eBay to manufacture such a beam combiner using a semi-reflective deformable membrane mirror, as shown here. Those mirrors, coupled with pneumatic systems, they are able to provide you the focuses that you might be interested in your application. For the sake of time, I will skip the details of the fabrication and control, but we'll jump to the final implementation. So as shown, you can see the final photograph. The final implementation's photograph is in the left-hand side. And using our prototype, visuals generated at different depth levels on demand. And this loopy clip is just showing you that capability. As you change the focus, the teapot is also, moving in depth. And in 2019, we started to play around with this idea of like, how do we take all these varifocal displays and make an even better display with even better resolutions? So our new solution is called a foveated varifocal display. As the field of view of a near-eye display will get larger and larger, number of pixels will dramatically increase as well. So this causes a major issue in driving these pixels, both in the case of hardware and software. Humans perceive sharp visuals only at the locations where they are gazing at. Basically, we get high-resolution images only at our foveas. Peripheral parts of our vision are in a much lower resolution. A display that can mimic such a behavior can fool a viewer and can make a viewer experience the same visual experience as if the display has all the pixels. So I should also mention the current foveated display products that you can find, like the one from Vario, targets virtual reality, whereas in our case, we are targeting augmented reality. And I want to also mention that these displays that you can buy right now, they cannot steer the foveal part on demand with a gaze tracker. And they cannot change the focus in hardware, while their form factor is quite bulky. So we come up with a solution as a picture-in-picture foveated display with varifocal capabilities. So our optical layout is shown here. As you can see, there is a projector on the right-hand side projecting images on a holographic optical element. That holographic optical element provides us a small eye box with sharp images. And then we have a second mechanism, a display at the top of all this structure that is providing us the high resolution part. And it's also statable, so it's basing on the classical birdbath optics in this case. So all the ingredients in this implementation are designed and assembled in-house. And we also, this is just a visualization, we also made this happen in real life, the final implementation led to a form factor as shown in these photographs. In the left top photograph, you can see the final wearable design prototype. And for the ones that are not in this field, packaging varifocal and foveation into glasses form factor is an amazing achievement. Not only in academic means, this is also a big step for industry too. And finally, this photograph will help you and will give you an idea about the visuals generated by our prototype, matching the visual acuity of human eye. So zoom-in photographs are also provided on the right-hand side to show the transition between high-resolution regions and the low-resolution regions. Before I conclude my presentation, let me inject one slide about an upcoming work at IEEE VR 2021. So far, we have seen an ordinary projection devices with large screens, and things have evolved into augmented reality displays, as we discussed. So, with increasing functionality of these augmented reality devices and designs, it's getting more complex and it's getting more challenging to design these displays. So we ask ourselves this question: how can we remove all these components from an ERI display while providing more functionality, access to computational resources, and power resources? To give you an idea, if you buy a headset that is untethered today, it can work on battery maybe an hour or two, but how can we break that limitation? How can we provide more computation to a display? So we have invented a new display type that we call as beaming displays, that is able to beam images to a user from a distance on demand without forcing user to wear a computer or a battery on his face. For greater technical details of this project, please visit our talk at IEEE VR 2021, which will be held next week, and download our paper from IEEE's website. So back to the conclusion of the entire presentation. Thanks to all my collaborators, we investigated on solving vergence accommodation conflict in the context of augmented reality MIRAI displays, while decreasing the computational complexity and improving on form factor and resolution. We introduced two varifocal systems, and we show that we can turn those varifocal systems into foveated displays. With that, let me stop here as we arrived at the end of our presentation. Thank you for listening and paying attention. I'll be more than happy to take your questions.
Thank you, Kaan. It's a great presentation. Now the floor is open for questions from the students, from the other attendees. You can just unmute and ask. I think we have a manageable crowd, so you can certainly do that. Let's see who wants to start.
Hi, Kaan. Jeremy Goodsell. Thank you for the talk.
Hi, Jeremy.
I had one question with regards to implementation of varifocal with respect to waveguide combiners. So I know it's not done very often because with the pupil replication, you could get artifacts with like the same image appearing at multiple different focal depths with the different pupils. I want to know if you have an idea of the benchmark of like how close can you get before those kind of effects start appearing.
Let me first see if I understand your question correctly. You're asking if we combine waveguides with varifocal mechanisms.
Yes.
Would that lead to a practical implementation? Is that a correct understanding? Or like, what are the challenges you're asking for?
Yeah, what are the challenges? Like because it seems like typically for the waveguide combiner, you just project to infinity, your light engine is projecting to infinity. You bounce around your waveguide and that comes out and you're just at infinity. So what holds you back from doing a varifocal, moving your light engine just closer to your collimation optics?
So waveguides, they have different type of solutions, of course. When you say varifocal and waveguides, the first thing I can think of in terms of literature is the work from Hong Hua from Arizona University. if you can find her papers about waveguides and varifocal displays, you will see that this is highly possible. What they do in their case is they have a micro display that is in front of a total internal reflection based waveguide. And it's an element that has an entrance like a prism with some focal power. So if you change the location of this micro display with respect to this waveguide, you will get the virtual image to appear at a different level. So this is one solution that I am aware of, at the very least. But I should maybe probably also talk about holographical optical elements as well. There is also one characteristics of holographic optical elements that one can use for waveguides. You can cascade them, and they are recorded such that they replay when you just shine the right optical beam. So why is this an important feature? It's obvious that like you can record holograms for different beams in space, and those beams can register different focal depths for you. So if you have multiple cascaded holograms, let's say, and if you ignite them, if you provide the image from a projector that is moving in space, in principle, you should be able to generate a display that is varifocal. And you can do this with by combining waveguides as well, because we know that waveguides and holographical optical elements go well because there is this other version in Hololens, which is not complete the holographic optical elements. It's using diffractive components, but it's something along the lines of the same story. You can have a total internal reflection waveguide with an outcoupler that is designed to provide you the correct focal depth, and you can provide beams in this waveguide that will register different depths. It can be done either just moving the source with respect to waveguide, or maybe you can use some sort of mirror device, active mirror device, to change the location of the angle that the display is using, the projector is using with respect to waveguide. And you can use such features to create a varifocal system out of using waveguides and holographical optical elements. There is also another solution that I'm aware of related to waveguides. Some people like to use cascaded mirrors. I'm trying to recall the name of the company. It's an Israeli company. I think Google invested in them. Sorry, I'm blanking with the names, but
Loomis?
it's a Loomis. Yeah, Loomis. Yeah, thank you for reminding. So in their solution, everything is more or less fixed, but I can imagine a version where you can have multiple different sources of light, let's say, and your mirrors, your cascaded mirrors, may register these different light sources to different depths. Of course, this may mean that you need unconventional cascaded mirrors with some optical focal powers, and this might be challenging to design and manufacture in the first place. These are the things that I can, let's say, speculate in the design space of waveguides and varifocals. Yeah, hopefully this is an answer to your question.
Thank you.
You're welcome.
Any other questions?
I have a question. So Dr. Akshit, this is really interesting work. So I come from Brown University. I'm a PhD student in a lab working on trying to understand how humans see the world in 3D. So my question may be naive because I come from a bit of a different space. I'm wondering if you could tell me a bit about, so this seems like really cool work, the varifocal displays. I'm wondering if you notice or have quantified potentially, say, perceptual distortions of the rendered objects, and if that might, say, vary with the different focal distances that you're rendering. Does that make sense as a question?
Yeah, it makes sense. I think I understand the gist of it, and your question is very valid. Because let's forget about augmented reality displays for a second. If you use a magnifying lens in front of a screen, and if you change the distance in between the screen and the display, and this will immediately cause your pixels to be registered to different places in space, that means you need a graphics pipeline that understands basically how your pixels are shifted and what are their forms now. Because if a pixel is at, let's say, at a larger eccentricity, it will appear more distorted. Therefore, it consumes a larger space in your field of view. and you have to account for that while you're rendering content for such a display. I think that's one thing to be considered, geometric distortions. And these works actually actively changing the geometric distortions that has been geometric distortion corrections that has been applied on the final image as it changes the depth. But there can be other cases like focal surfaces, for example, where things are a little bit more funky because you have a surface that is no more flat anymore. Maybe you're trying to show depth levels that has some variations over a surface. In those cases, you can still do active compensation. That is highly likely, and there are papers in the field which you can find if you look into SIGGRAPH 2018 focal surfaces paper. You'll find out more about the greater details of how does one fix geometric distortions in such a display.
Thank you.
You're most welcome.
Other questions?
Hi, Kaan. I have a quick question.
Hi,
Thanks for your nice presentation. In one of the approaches that you discussed, you mentioned about moving the beam combiner to change the depths of the virtual objects. I want to know more about the trade-offs in terms of the delay and the accuracy.
Yeah, that is an awesome question. So maybe I should first have this quick reminder about the human eye. Human eye, when it accommodates, change its focus from one depth to another, it can either take 300 milliseconds or it can take a second overall. And if you want to change the depth from one plane to another, of course, you have to take into account that human eye responds to focal changes in a very slow manner. So this means we don't have to change the depth maybe. Of course, this is also a vision science question. I cannot answer on their behalf, but from the optical design stand, this kind of suggests me that I can now change the depth by just following the delay of the human eye, and it can be in the ballpark of 300 milliseconds to a second, which is quite long. You can even use mechanical stages for doing these things. Will there be any perceptual outcome of that? Like, will you be perceiving the change? Is it still an open question? There's more research needed to be conducted in that front. So varifocal displays and how we perceive the depth change with the gaze tracker, that's still an open question. About the delays, we basically applied this rule of 300 milliseconds to a second by just looking into the literature from 1960s, if I remember correctly, where they measure the delay in the eye. But is that an answer to your question, or were you asking something differently?
I got it. Thank you. Yeah.
Okay.
Other questions?
Hi, Kaan. It's Suleiman from Luminate. How are you?
I'm doing good. Thank you so much.
Good.
How are you?
I'm good. I'm good. I had more of a question on the last topic, and that was the projection display.
Mm-hmm.
Do you see that being used in more head-up display applications where the viewer is stationary?
Yeah, so this is also a great question. I envision this. I mean, I didn't give the greater details in this slide, but I envision this as a steering projector located at some location in the room, and you can move freely with respect to that projector. And you as a user is varying just a passive optical component, nothing more. And it can be in the form of a birdbath optics or any other optics that we can rely on in the long run. So in this passive variable headset part, I hope you guys can see my mouse cursor. This one is showing the most simplistic approach, basically, where you shine the image onto this diffusive screen, and this image is being just magnified with the help of this birdbath optics. This is more geared towards a scenario where you can move freely in front of a projector, without having to wear, all these electrical components or batteries or, computational resources.
I see.
So you can equip your projector with the best graphics card or the best CPU or the best computational resources, or you can just plug it to, a socket and you'll get all the power budget you want, of course. This is to free the displays from the limitations of computation and the power budget.
Okay, not the optics then. Okay, could someone put a link to that paper in the chat section?
So this isn't online yet, but if you go into IEEE Explorer,
Okay.
you'll find out beaming displays as an upcoming paper. I think they are listing
I
it
see.
right now, but I'm not sure if they are sharing the PDF. If you can, search it within the next 2 weeks, you'll be able to get your hands on it, I think.
Okay, so it's relatively new. Okay, great. Thank you.
You're most welcome.
Other questions? Maybe I'll ask one as people are thinking. So Kaan, I see how hardware, optics, as well as computation interact very nicely with our work. So I'm interested in asking for your vision on the role of computation in the future and how that will expand. Of course, it can be in many directions, but I'm primarily interested in computational imaging and things like machine learning, and whether you see a role for computation in these directions in the future.
Yeah, so that's a great question. Recent papers, actually, the ones related to holographic displays, I think, are very interesting in my opinion, because it opens up a gate to a new type of display that has superior capabilities in terms of resolution, field of view, and also it promises, interesting features like true 3D and so on. These holographic displays are quite interesting. The hard part about holographic displays is how you calculate a hologram, and that's a computationally expensive process. And machine learning, I mean, the recent papers in SIGGRAPH and Nature, the one from Stanford University, Gordon Wettstein's lab, SIGGRAPH 2020, and the one from MIT, I think that appeared 2 weeks ago, Shi et al. These are works that combines machine learning and holography and near-eye displays into a single paper. And that's a very exciting opportunity in my point of view, because there can be many different ways to calculate a hologram. There can be many different ways to show a 3D image to a user, and we can look into all these problems in computation space regarding how you calculate holograms. That's a nice opportunity for where you can combine machine learning, computational imaging theory, and displays all together. Not sure if this is an answer to your question, but that I personally find it as an exciting, interesting direction.
Yeah, absolutely. Thank you.
Yeah.
Anybody else? Questions? I don't see any. Last call for any last questions. Okay, I don't see any. If that's the case, Kaan, thank you so much for
Thank you so much for having me.
Presentation and answering our questions. And our students, I'm sure, will learn a lot from both the contents of your presentation as well as your career path. We greatly appreciate you accepting our invitation and giving this talk. Thank you so much.
Thank you, guys. Thank you very much.
Have a great day. Bye.
You too. Bye.
Thank you.